Hi there, everyone. This is 11H. This is some more techniques of integration where we're looking to find more complicated areas. So up until now, we've just worked out the area, say, for example, if we have a look at this one, up until now, we've worked out, say, for example, the area underneath the curve for f of x, so this thing here. And now we're just extending this to say, well, if you wanted to work out the area which is trapped between two curves, you'd need to do the area underneath the blue curve between A and B, and or the top curve rather, and take away the area of underneath the bottom curve here, the red line. So that's pretty obvious, I guess. That's this formula here. But the kind of useful thing about this is that we can combine it. So we can combine this thing to become this formula here. Now that's pretty useful because it could be the case that f of x might be, let's say, I don't know, x squared plus 2x plus 1. That could be your f of x. And then g of x could be something like x squared I don't know, plus 3x. And so instead of doing two separate sets of working out, you can make life a lot easier by just subtracting your two functions to start off with, and then coming up with one function inside. So it makes life a fair bit easier. Okay, there's a few questions here, and I'm going to go through them fairly quickly. So let's take a quick snip of question example 14. I won't write anything much on this, I'll just talk this one through. So this question says, sketch the region bounded by these two curves here, and x is equal to 3. So you can see that this has been done here. You can obviously use your GDC in this case in order to work this one out. X is equal to 3 is this line at the end that's needed to come up with an end to this region. And you need to sketch the graph because you're not really sure to start off with which one is going to be above which one. So you need this to be the right way round. So for our formula, it's f of x take away g of x. So in this case, it's going to be this one, which is f of x, because you can see that this is, if you like, this is the function which is on the top. And we know that because a square root function looks like, well, square function kind of looks like this, parabola, and a square root function, let's just do the square root of, that's x squared, square root would be looking like this. It would be a reflection about y is equal to x. That's the positive square root. There might be a negative square root function as well, of course. Okay, so let's just take some of that back. You're going to need the A, as in where this region starts, and you'll need to do that. You'll need to find that by finding the point where the two functions cross, and obviously you can do that using your GDC by looking at points of intersection. Once you've done that, it's pretty straightforward. You put the function inside there. You can just do a subtract of this function. So you can put it inside the brackets in this case. Now, that's not easy to simplify, but you don't need to if it's not asking you to show your full working out. And then, of course, you can put that one in your calculator. Right, hopefully that is fairly straightforward. Let's have a look at another one then. So here we go. They start talking about, this is a pretty good point here. It says, this expression is valid even when either of the curves is below the x-axis. Okay, so let's just take this one here. Okay, let's just take a copy of this. Okay, so it's saying this is valid even when one of the curves is below the x-axis. So you can see that we've got sometimes two of the curves underneath the x-axis in this case. But the reason why this is working is because this is essentially f of x minus g of x is essentially a slice of height. And so f of x minus g of x is like this height here. And if you remember where this all came from, it was about considering small rectangles taken to their limit in terms of their size, their width. Okay, so the limit, their width becoming 0. So those rectangles still exist. If you're doing f of x minus g of x, you're still getting a difference in the height there. So this function is still working here, of course, right? So the only thing it says, though, is that if you're looking for the area which is bounded between these two curves, and you're not sure whether or not you should, which one would be on top, because you can see here they change, the functions change as to which one's on top, then in this case, you would do the absolute value of those things. So that's always taking a positive answer to find that area. If you did, say, for example, this was your f of x and this was your g of x, and if you did the function straightforward, this would give you a positive area here, but then a negative area here. So to avoid getting positive and negative areas, if we just take the absolute value of f of x, take away g of x, then you'll always just get a height. Whatever that height is, it will be given as positive. And so again, that's going to just work out the area of that section. Right, okay. You could do it a different way, of course. You could actually just use the regular function here, and then you could say, you could work out this one, take away this one between this point, and then the other way around between this point, and then you need to do the other way around for this as well. But that's obviously much more complicated. Right, there's not much more to say about this one really, other than, of course, you've got to remember your absolute brackets. And they've given us where x starts and finishes. So those are your limits at 0 and 2 pi. And of course, you can type it into your calculator. Nothing tricky there. Okay, let's just have a look at the next one. Okay, so that's just a little explanation of that one as well. Okay, and so this is pretty neat. They start saying, what about finding the area between the curve and the y-axis? Okay, so in the example they're going to look at, example 16, they're going to say, well, what about this blue area here? Now, you could actually work out that blue area by working out the area underneath it and taking away that area from the rectangle that it sits in. I'll show you that again in a second. But we've got another method of doing this, and it's just basically to flip your axes around. And so it's saying, let's do this in terms of y. Let's do it with respect to y instead of with respect to x. So the formula is the same as your previous formula. So there's nothing different here. They've just said, if you want an area, make sure to take your absolute values, because of course you can have positive or negative area depending on which side of the axis it's on. And this is just the same as what we normally do with f of x in terms of f of x and then a dx there. So this is just normal. It's just they've switched the x and the y. Okay, so let's actually do this question. So let's take this one and let's just do the whole thing. Okay, now it says you can do it on the calculator, but let's do it without a calculator, in fact. So find the area of the region which is bounded by this curve, y equals x squared, and the y-axis. And this notation here, by the way, just means x is in between -2 and 0. And the square brackets means it can also be equals to. If you see curve brackets, it means that you're not allowed the equals to as well. So this is just saying that x belongs in this region. This symbol reads as belongs to, okay, or is an element of. Okay, right, so let's take that back. Okay, so obviously the graph that you need is from your y equals x squared. Let's just put that in roughly. Okay, and let's put in that top point as well. We've got that point here, 4 and -2. So we've got -2 there, we've got 4 up here. Okay, so that's the sketch that we need. And the area which is bounded between this and the y-axis is obviously this area here. Now, what I was saying a moment ago is what you could do is still work out this area if you integrate it with respect to y, with respect to x, and do that between -2 and 0. However, we're going to do it the other way around here. So what are you going to do? Well, you need a function in terms of y. So we need the opposite way around, basically. So we need x in terms of y. Now, when we do this, we're going to say, let's just take the square root of both sides. X is equal to the square root of y. And on the left-hand side here, we're getting out we're getting out negative values for x. So, for example, when I put in 4 for y, square root of 4 obviously gives us 2, but that would be the point over this side. So the point over the other side is minus 2. So this needs to be negative here, because it's essentially like, when we're reflecting this, it's this part being reflected. It's the negative square root, which is being reflected. Okay, so right, find the area of this. Right, I'm taking a bit of time on this one. There we go. So we've got minus the square root of y. We've got dot dy, and it's between minus 2 and 0. Oh, but hang on a second. For y, it's between 0 and 4 because the axes are now the other way around. We've got between 0 and 4 there because it needs to be in terms of y, not in terms of x. Now, if you're unsure about that, you can put in minus 2 inside into here, of course. So minus 2 equals minus square root of y. And then you're going to need to divide by minus 1, square both sides, and you'll get y is equal to 4. So that gives you your answer there when we put in the minus 2. You have to interpret this a bit as well, because clearly this starts at minus 2 and ends at 0. But we want it to start at 0 and end in 4. So it's switched around. And in fact, that has the impact of changing your answer to a negative by switching your limits around. Yeah. There you go. But in this case, actually, it doesn't matter because they want us to find the area. They actually want this thing here. They want the modulus of this thing, which is what they tell us in the book to use as well. They say use the modulus of this thing too, because we want a positive value. Now, actually since this is always positive, taking the negative of something which is positive and then doing absolute brackets actually just gives us the same answer as doing the square root of y. So we've just made all of our answers positive there. They were previously negative, now we've made them all positive. So I'm doing this without a calculator. You can obviously just type that into a calculator. So there we go. And in your next step, let's just get rid of that for a moment. Take it down here. So my next step would be to write this as to the half. So use plenty of steps here. And then you can do your integration. So then you've got y to the power of 3 over 2. So we raised it by 1. And divide by that is the same as timesing by its reciprocal. And that's now, we need to work that out between 4 and 0. Now your next line of working out is to substitute the 4 in. So we've got 2/3 to the power of 4 to the 3 over 2. And you've got take away that thing with substituting in 0. Now, obviously, the second part is equal to 0. Now, the first part you can work out without a calculator as well, because the square root of 4 is 2, and then cubing it brings us to 8, and then 8 times by 2/3 gives you the answer of 16 over 3, which is 5/3, which is the same as the answer in the book as well. So that's a little bit messy there, but hopefully you can see that. Okay, right. So there's that question done as well, and then you're on to the exercise. Thanks for listening here today, guys. Obviously, keep asking questions in class, and see you tomorrow.